Okay, this is Logs Day 7, and we're going to be doing some application questions after we get through a few reviews. This, right there, I lock in on that part, personally. As soon as I look at this problem, I look for the clump, that log part right there. Do you know what that's equal to? 3. Why? Because the 27 could be changed into a 3 to the third, and then the power is the answer if these bases are the same. So that's just a 3. So then this becomes 6 times 3 plus 5 equals 5x minus 2. If you tried to rewrite this one, it would be really a pain in the neck. First, you'd have to get the clump alone, subtract 5, then divide by 6, then you do the rewrite, and then you'd have a power, an x in the exponent, and it just wouldn't be near as good. So if you can identify the little log part and figure out what it's equal to, all of this right here becomes a super easy equation you've done since like 6th grade. Okay, moving on. This one you can't just figure out what this is because it's got an x in it. So then you do have to get the clump alone. So everybody get the clump alone on this one. And then do a rewrite. And then put it to a power to fix it so x is getting alone. That's the whole goal here. Once you get the clump alone, then you got to get the x alone. All right, I'm going to pause for a second while you try this one, and I'll have you compare with the person I pair you with. Okay, your first step on this one, divide by 2. Once you've divided by 2, this is gone. That is negative 3. Rewrite, that to the that equals that. 3x to the negative third equals 64. I just made one of the classic mistakes that almost everybody makes. Can anybody tell me? Many people made this mistake on the test. Yes. Why does it matter that I have parentheses? It really does. I mean, you might think it doesn't matter, but it does. Because now both things are being put to the negative third power. Without parentheses, then only the x is being put to the negative third. It needs the parentheses. Whether it's in the base or the argument, those parentheses are the difference between an A and a B in this class and the next test. Because that's the little stuff that gets it marked wrong. Okay, so now I've got that parenthesis in there. Now I need to put both sides to the negative 1/3 power. And hopefully you can do that part in your head. Odd roots don't need absolute values. So this just cancels this. And I got 3x equals cube root of 64 is 4, and then flip it, 1/4. Then you multiply both sides by 3. The answer is 3/4. Raise your hand if you had 3/4. Oh, must have did something wrong. Oh, I tried to do it in my head. That's the other really common mistake, is just little putsy stuff like that. Divide by 3 on both sides, and if I'm going to divide by 3, that's like timesing by 1/3, and then x equals 1/12. How many had 1/12? All right, good. I didn't sucker anybody into that. Okay, move on to this one. I could see if I can do this without having to rewrite, or I could just rewrite it. Either way works. If you can make that into a 2/3 to a power, then you can just replace this whole thing with whatever the power is. That's an option. Another option, you rewrite it. I have to say, if you're not sure, rewriting is probably the best place to start. All right, if you go with the rewrite option, this and this need to be the same, so I'd pick 2/3, because then the left side's already done. And then this is equal to that, and this needs to equal this, so I make it 2/3, and this has to equal this. And everything's good so far, except this really doesn't equal this yet. 2/3 to the what would be 9/4. Negative second, you're right. So then, that has to equal that, since the bases were the same, and x equals -2. Oh, it's a oh, thank you. It's a rewrite right from the beginning. My bad. That to the that should be a negative x, which makes this a negative x, which makes that a negative x. So x equals positive 2 at the end. Thank you for catching that. Oh, just a little off. Not quite on my A game yet. Still feel like I didn't get good sleep last night. All right, moving on. So this is a cool example of a real world thing that I looked up this summer. I was looking for examples of really steep beaches and really flat beaches, and I got some nice pictures here. So what makes a steep beach? In other words, this beach, if you look at it, if you like ran down to the ocean, you get it would be a very steep like ascent down to the ocean. There's a heavy duty slope there. It's not flat at all. It's very steep. What are your guesses on what makes that happen?
Something to do with logs.
Okay, that's a good guess. What do you think makes some beaches steep and some beaches very flat? I'll give you an example of a very flat beach. It's like Fort Myers Beach. It's really, really, really flat. And it's like sort of like walking on a tabletop. And then the water just happens to be like right up next to it. Yes?
Would it depend on how far the water goes?
How far the water goes? What do you mean by how far?
Like if you go there and it keeps going, then it's going to go like down and it's going with the water.
So are you saying that the water level makes, is that what you're talking about? Like how deep the water is?
Kind of saying that if like the waves come out to the sand, at that moment it goes to a point and it keeps going to the same place, so it brings back some sand with it, so it's going like steeper and steeper.
Okay. I get you, the wave action, and that totally makes sense that wave action would, would give you a steeper or a flatter beach. But believe it or not, if there's something else that if you, no matter what the wave action is, will cause the beach to be steeper or flatter. Yes? Yes, the size of the sand particles. You are correct. If you've ever been, this is an example of a beach that's actually in, I think it's in Central America. But the one that maybe more people would have been to would be in Hawaii. How many of you have ever been to Hawaii? All right, the 3-4 of you. All right, so if you've been to Hawaii, you probably may recall anyway that the sand on those beaches is much bigger diameter. It's like I remember picking up a handful of sand in Hawaii and thinking, man, this is like little tiny rocks. That's what the sand was like. They're really big chunks of sand. That makes a steeper beach. Fort Myers Beach, on the other hand, how many of you have been to Fort Myers or a beach in that southern Florida kind of area? All right, it's a lot of people. Okay, and that's really fine sand. It's the kind of sand that like it's hard to get off your feet because it's so tiny. And that kind of sand, that makes a very flat beach. Super tiny particles. So specifically, I looked up this little formula, and this is the formula that tells you, with a log in it, how steep the beach will be based on how big the sand particles are. All right, so basically, we've given you a formula, and there's only two spots you could stick stuff, S and D. Just to clarify, S is in terms of D. When I say in terms of, means there's a D in my answer. Okay, S is in terms of D. So, of course, if they give me the slope, I'm going to put it in for the S. And if they give me the diameter, D, diameter of the sand, I'm going to put that in under D. Okay. So you got to be careful to read like the problem to know exactly what S is. S might, in this case, I knew it was going to be the slope, but it says it right here at the beginning. There are some formulas, like here's one from pre-calc, S equals theta R. Which one of those do you think is the radians? Yeah, and it's not. Which one of those do you think is the arc length? Theta or R? Nope, it's the S. So anyway, the point is, if you don't have like the directions, this is a famous formula from pre-calc. You'll all know it next year. This is the arc length. What? Why didn't they pick A? Well, they didn't. And this thing is in radians. It's an angle in radians. And then this other R is the radius. The point is, you have to kind of look at your formula and know what words are associated with what variables. So here it says the slope is S and the diameter is D. And we try not to fool you on these, but just be aware we could have made the slope D and the diameter could have been S. You just have to read the problem to make sure. All right. So right now, how do I solve this thing if I put in 0.25 as the diameter? Well, and the 0.25 goes there. And all of a sudden, the problem is just all of that, which a calculator could do for you. Everybody grab a graphing calculator. I'm going to pause for a second while you get yours ready. If you forgot it quickly at hand. Remember, you don't have to type in log base 10. Your calculator does that automatically. Just log of 0.25. And I hope you know the order of operations. You do not add next. You have to multiply this times that before you add 0.159. Make sure you do it in the right order, because if you don't, your partners won't match yours. Okay, so ask the kid sitting next to you, if you need to borrow one of my calculators, come on up, leave me some collateral, and borrow away. All right, so for those at home, here's what you should have done. You should have taken your calculator and went log 0.25, then times it by 0.118, then add the 0.159. Notice the order is really important. And what did you get for part A? Say that again, point what? 0.9. And what do we just figure out? The slope of the beach. Now think about this. Is that a steep slope? 0.09. No, that's very, very flat. Does it make sense? You had sand that was being measured in millimeters. It's pretty. It should be not very steep. Okay, quarter of a millimeter, just for perspective. A millimeter is the thickness of a dime, and so then it's 1/4 of the thickness of a dime is the diameter of the little sand particles. So, all right, the average diameter if the beach has a slope of 0.125. Okay, so then where do you put that? You put it in for S, and you say this is 0.125. And then you solve it by, well, get the clump alone. That's the clump. So I subtract this, then I divide by that, and at the end it's going to say log base 10 of D equals, what'd you get for that decimal after you? Negative 0.28, what? Good enough. And then it's a rewrite. 10 to the power of that equals your diameter. What'd you get for a final answer on that last one, Mr. K? Don't have it yet? All right, keep working at it. Mr. R. Did anybody else get 775? All right, that seems off a little bit to me. That would be really big. Okay. So I'll say what we were supposed to do again, since the first two people I talked to didn't know. What we're supposed to do is put in 0.125 right here and then solve. So you should have subtracted 0.159, then divided by 0.118. Who's got an answer they're confident in? Mr. P? 0.515. Who had 0.515? All right, I think that's probably what we're looking for. And at the end, how did you I guess you just put 10 to a power to get your answer, right? All right, good. Okay, so now just think about that slope for a second. Slope of 0.515. Wait a minute, sorry. The diameter of 0.515. That's a lot bigger than our other diameter, which makes sense because it's twice as big as sand and it's got a lot bigger slope. See how the slope went from 0.09 to 0.125? That's like 125 compared to 9. It's a lot bigger slope, and therefore it makes sense it would have bigger sand particles. Okay. Another application of logs. I was trying to look for good ones, and I found this. It's about decibels. Basically, whispering has an intensity of 5.4 times 10 to the negative 10th. That's an incredibly quiet, noise that you can barely hear. It's kind of an interesting thought. People have been talking about, being able to hear things that other people can't hear. Have you ever noticed that if you're in a completely silent environment, you can hear things all of a sudden that you aren't used to hearing when it's totally quiet? And there's some talk of Buddhist monks trying to attune their hearing so well by sitting in silence and focus that they can hear grass growing. That'd be kind of a cool concept. So anyway, if you had incredibly good hearing, you obviously could hear bugs like you can hear mosquitoes. That's not too tough, but you can hear other smaller bugs like on a summer day. All right. As opposed to, of course, on the other end of the scale, there's incredibly loud noises that are it's like you can't just say take the bug scratching its wings noise times 10 or times 100 or times 1,000. It's like times 1,000,000 to get like a jet engine kind of a noise, right? So the difference is so huge. That's what logs are good at, is taking a range that's so huge from like the quietest noise you can barely hear that you'd have to times by like 1,000,000 or 100,000,000 to get up to the loudest noise that you've ever heard. And they take that scale and they bring it down to a nice simple 10-point scale, or maybe in the case of acids, a scale that's, 14 to 1, yeah, or 0 to 14 or something like that. Anyway, so keep in mind humans can only hear from 20 decibels to 2,000 decibels. Does that mean that there aren't noises that are quieter than 20 decibels? Of course, there's noises there that are quieter than we can hear. Can anything hear better than us? Oh yeah. And just for perspective, elephants can hear over 12 miles away because they speak in incredibly low. They can make noises that are so low that we can't hear them on the range. Just these like low rumbling kind of noises. And anyway, that travels through the ground really well. Really low noises can travel through the ground. And so they pick it up through their feet, believe it or not. They can hear the noise through their feet, which are touching the ground. They can hear the other elephant from like 12 miles away. I thought that was cool, and I was looking this up. All right, so anyway, we've got this little formula, 10 times log base 10 of I over 10 to the negative 12. That obviously is a insane complex formula, but a careless whisper has an intensity of that. How many decibels is that? Well, where should I put that? The D or the I? I, intensity. And so that goes in right there. And you'd have 10 times log, if I don't say base 10, it'll mean base 10, of 5.4 times 10 to the negative 10th over 10 to the negative 12th. That is some heavy duty, like you'd have to take some time to put that into your calculator. But it's not impossible. You can take the log of that and then you times it by 10. And that'll tell you your decibels. Go ahead, take a second, type that thing in. If you forgot how to put in times 10 to the negative 10th the fancy way, just put it in the slow way, it'll work. Just gotta have, if you want to remember, times 10 to the power is the EE button. If you want to try it that way. The double E button puts things 10 to a power. But otherwise, I'd want to put that in parentheses, and I'd want to put this in parentheses also. And then when you're all done, you can take the log of that number. So once you have it on your screen, and it's some crazy 000479, or maybe it's even EE3 or whatever it is, once it's on your screen, then you can say log, and then bring back that crazy decimal by saying second answer. The second answer is right above the negative key on your calculator. That'll bring back your most recent answer. You go log of, second answer. Or you can just type in a log in the first place, and then be really careful with all your parentheses and stuff. And see if anybody can actually pull this off. I'm guessing less than half of you can do it, but more than half of you will probably make a dumb mistake. I'll pause for a second while I give that a try. Okay, I'll tell you, if you got an answer in the 20s, you probably did it right. Anybody get an answer in the 20s? Ooh, lots of people got it. I'm impressed. 27.324. All right. So now this is a weird scale. 27 decibels for an incredibly quiet noise like that. The way I understand the decibel scale, you go down and down and down. So if you get a loud noise, it's like 1 decibel. Now, I'm not positive of that. I just know from looking at my stereo, because my stereo tells how many decibels it's putting out, and it's always like inverse from what I would expect. And to some extent that makes sense because we're dividing this by 10 to the negative 12. Although, wait a minute, dividing by a really tiny number should actually make it bigger. All right, gonna move on. My head's gonna explode if I think about decibels anymore. And the last thing we have to do is talk about tables. All right, I don't expect you to know if I put a 4 in for this, what log base 3 of 4 is. You're not gonna know that one. So again, you want to choose wisely. First thing I would do if I were you is to take this and do a rewrite of your equation. Something to the something equals something. It'll be way easier. Do you get it's 3 to the what? Y is equal to x. 3 to the y equals x. Do you get in this weird world that it would be smarter to pick a y and figure out what the x comes out to be? Yes?
Why do you want to pick, like,
Things that work nice.
something equals 3 or 1 or maybe, like,
Yeah, so give me some options. Like, what do you think is a good y to put in there?
0?
0 is a good choice because 3 to the 0 equals what? 1. Good. And then what else could I put in for y? 1, because 3 to the 1 is easy to do, so I'm putting in a y is 1. And what does it come out to for x? 3. And then let's keep going. Negative 1 is the other one that we like to pick, because that just means flip it. So then you take 3 and you flip it, and you get what? You just have to be careful that you're not sticking the numbers in for x that you meant to stick in for y. Because we were choosing y's. We chose 0, 1, and negative 1, and those are always really easy ones to do. Because anything to the 0 is going to be 1. Anything to the first power is just itself. And anything to the negative 1 power is just take the number and flip it. So those are the easy ones to do. Could you do something like 2? Absolutely. I can put in 2 there, because 3 to the second power is 9. So there's another combo. Yes, sir.
The way that would require that you don't rewrite it is
Uh-huh.
knowing the
Yes, knowing rules. Like if I didn't have to rewrite this, you were absolutely right. I'm just telling you that that was the way it works for a lot of people. You don't have to. Like you said, if you know these rules, if I put in y is, or x is 1, I would choose that logically because when you won the argument, you get nothing, right? See, if you put a 1 here, it will work nice. And if you put in a 3 here, it works nice because you know those rules that it's got a power on it, and the power is the answer. So if I put in a 3, I get a 1. Okay, if I put in a 1/3, that's a little harder of a stretch to think of putting in a 1/3 and then getting a -1, but that works. And the last one is if you put in a 9, you would get, that 9 is really like 3 squared, and therefore the answer would be 2. Okay, so you can do it either way you want. I don't care, as long as you make a list of points. And once you got your points, you just have to slap them on the graph, and then we should try to figure out what logs kind of look like here from looking at these points. So let's everybody graph these points. 1, 0, 3, 1, 1/3 -1, and 9, 2. All right. You remember the exponential graph that would go like this? Well, this doesn't look like that, does it? But it's similar. It goes like this. Now, I like to think of it this way. What are logs? Logs are basically trees that have blown over in the wind. Look, it looks like a tree that's being blown over in the wind. See, it was planted in the ground like this, nice and straight, and then one day the wind came along and blew it over. Okay, anyway, however you want to remember it, logs always go through this spot right here, just like our exponentials always went through that spot right there. Same kind of reasoning. Exponentials, we were putting in 0, and then when we had an x in the exponent, it was like this. We had an x in the exponent. When the x was 0, it had to force it to be 1. There's something like that for logs. I want you to think that through for a second. Why does it always have to hit that green spot right there? That's that dumb little saying. Yes? When you won the argument, yes. The argument is this x. When the x is 1, in other words, finish it. You get 0. You get nothing. So 1 goes with 0. Okay, so that spot's going to be on your log graphs. Could I move my graph up so it's not there anymore? Sure. All I'd have to do is take this graph right here, and if I want to move it up so it won't touch there anymore, I can say like +4. Now the whole graph has to move up 4. All the dots go up 4. So you can eventually get away from that spot, but the parent graph of it is always going to go through there. One more thing. Do you remember on our last test, some of you got burned for the asymptote and not having the asymptote in dotted line form? I know some of you are a little bitter over that. I apologize, but I have to be the same as the other teachers, and they've all were going to mark off half for it, and I had to say, I guess it's true. Asymptote lines are dotted lines. But I probably didn't make a big deal of it before. I'm making a big deal of it right now to remind you so you don't lose that point again. There's an asymptote line. It's a dotted line. Okay, and it goes right down the y-axis. Could it move? Yeah, I suppose if I move the whole thing to the left. How could I move the whole thing to the left? If in here I put like a +2, the whole thing would move to the left too. And then the asymptote and everything, including the asymptote, would move to the left too. Okay, so that would again be something like log base 3 of x plus 2. That moves the whole thing to the left too. This would move the whole thing up 4. So you can do the same stuff as you always have. We're moving it left and right. We're moving it up and down. You can even flip it by throwing in a negative in front of it. Would flip it up down. Then it would look like that, which is more confusing, but you'll be able to handle it. And that's actually what we're doing tomorrow. Okay, so moral of the story for graphing. You want to make a list of points like this. And generally speaking, log graphs look like this blue graph right here. And it's just that sometimes they're stretched more or less. Sometimes they're moved up or down. But that's kind of the parent. That was with a base of 3. We could have just as easily had a base of 2. It doesn't really, we just pick one to be the parent one because there isn't one true parent. The one that you use the most is log base E, which you haven't even learned yet. Log base E is that one where E is about 2.7. And it's this base that's really close to base 3. 2.7 and 3, almost the same thing. It's just That one is a special one, and you'll learn in calculus why E is so special. Okay, this one, would you just make me a quick move this? This is just the parent one, except it's been moved a little bit. If I were you, I would just rewrite this puppy and ask yourself, what are the parent points? And then take all the parent points, graph them, and then do these things to them. You're going to move them all to the right too, and you're going to flip them all. Okay, but first I would graph the parent points that we just had seconds ago. Same as on the other graph. Do you remember what those were? If you don't, you can just try them again quick. If I put in x is 3, I would get 1, right? And if I put in a 1 here, I'd 1 the argument, and I get 0. If I put in a 1/3 for x, if that's a 1/3, then it would be -1. And if I put in a 9 here, then log base 3 of 9 would be 2. Now, this is different than what I told you before on this topic. I suggested before that it was probably best if you just make your points right away. Let's a second here. There we go. I suggested before that you just take a chart like this and make a chart for that. But the problem is, I think that gets so complicated to try to make an XY chart directly from this that I think it's better to do 2 steps. I think it's better to make the parent one, which will be easy points, and then just move those points. Every point moves right to, and every point flips, and make sure you do a right kind of a flip. Does the order matter? Yes, it does. I recommend you start on the inside. But actually, in this case, it's a dumb one. It actually could go either way. The order in this problem could be inside and then outside, or you could do outside and then inside. So how do I move them all 2 to the right? I'm going to do it in green. 2 to the right of where it used to be. That's 2 to the right of that spot. This is 2 to the right of that spot. And this would be 2 to the right of that spot. And then I would draw it like this. That's 2 to the right. But I need to also do it up, down, flip. So then this flips down to there. This doesn't flip at all because it's on the line, and it can't flip over the line if it's on the line. This flips like that, and this flips like that. And now, I'll make sure I'm 2 to the right. Yeah, I'm off a smidge. You're right. It goes down 2. Thank you. It does look a little flat down there. There we go. And it's a really sharp turn there. How do I know that there's an asymptote line right here? Because it used to be right here, and then it got moved 2 spots to the right. So burp over here. And so then this needs to be adjusted just a smidge so it's not actually touching that line. There we go. So my final answer is the blue one. The green one was the move to the right. The blue one is it's been moved to the right and flipped. Final answer would be that blue one. All right, so the moral of the story. XY chart, only do it to the parent one. I'm telling you, if you try to make an XY chart off of this, it's hard to do. You can do it, but you're more likely to make dumb mistakes, I think. Your choice. So you just have to have an XY chart, and you have to have a graph. All right, now the only thing you haven't learned is log base E, I guess. I thought this was not today, but I thought this was tomorrow, but I guess log base E must be tomorrow. I don't think we need to do another one of those, so we're fine. Your homework for today, let's all look at together. You'll learn about log base E tomorrow. All right, so on number 1, I suggested on part A that you do that log base 5 of 125 first, because that part you can do in your head, and it's a nice simple number or less than 5. And then once you put that in, it's easy. On part 2, all you got to do is put in 60 in Chandler spread right there in for the A, and then you're going to use the log button on your calculator times a log of that. You're going to times it by 116, and then you're going to subtract 176 from it. That's all I have for you for today.